Hey students, today we are going to discuss about refraction and reflection by spherical surfaces. In this chapter, we will study the formation of an image by simple optical systems. We will assume the optical system to be made up of a number of refracting surfaces like a combination of lenses. In order to trace a ray through such an optical system, it is necessary only to apply Snell's law at each refracting surfaces. So, according to Snell's law, the incident ray, the refracted ray, and the normal lie in the same plane. And if phi 1 and phi 2 represent the angles of incidence and refraction respectively, then sin phi 1 by sin phi 2 equals n2 by n1. Here, here n1 and n2 are the refractive indices of the two media. And to discuss about refraction at a single spherical surface. Consider refraction at a spherical surface SPM, separating two media of refractive indices n1 and n2. Here, C represents the center of curvature of the spherical surface. And we will consider a point object O emitting rays in all directions. We will use Snell's law of refraction to determine the image of the point O. That not all rays originating from O converges to a single point. But if we consider only those rays which make small angles with the line joining the points O and C, then all rays converges to a single point I. And this is known as paraxial approximation. And according to Fermat's principle, all paraxial rays take the same amount of time to travel from O to I. So this figure represents the paraxial image formation by a spherical refracting surface separating media of refractive indices n1 and n2. O represent the object point, here O represent the object point and I represent the paraxial image point. In terms of the angles defined in figure, we have phi 1 equals beta plus alpha 1. That is exterior angle equals sum of interior angles. Beta equals alpha 2 plus phi 2 and beta equals alpha 2 plus phi 2, and from that phi 2 equals beta minus alpha 2. Use of the paraxial approximation, that is all angles phi 1, phi 2, alpha 1, alpha 2 and beta are small, so that we can write sine phi 1 nearly equal to tan phi 1, which is nearly equal to phi 1, where the angles are measured in radians. We can write sine phi 1 nearly equal to phi 1, which is equal to tan beta, which is equal to beta plus alpha 1, that is nearly equal to tan beta plus tan alpha 1. And from this, tan beta is h by r and tan alpha 1 is h by x. That is h by r plus h by x. Sine phi 2 nearly equal to phi 2, which is equal to beta minus alpha 2, nearly equal to tan beta minus tan alpha 2, that is nearly equal to h by r minus h by y. Here, the distances h, x, y and r are defined in figure, and we have assumed that the foot of the perpendicular capital D is very close to the point P. So that we can write OD nearly equal to OP, which is equal to x, and ID nearly equal to IP, which is equal to y. From Snell's law, we have sine phi 1 by sine phi 2 equals n2 by n1. Let it be equation number 1. Substituting the values of equation 2 and 3 in equation 1. Is h by r plus h by x by h by r minus h by y equals n2 by n1. Then on cross multiplying gives n1 h by r plus h by x equals n2 h by r minus h by y. That is n1 h by r plus n1 h by x equals n2 h by r minus n2 h by y. Then on rearranging, we can write n1 h by x plus n2 h by y equals h by r into n2 minus n1. That is h into n1 by x plus n2 by y equals n2 minus n1 by r into h, and cancelling h on both sides, n2 by n1 by x equals n2 minus n1 by r. That is equation number 4.